because lambda is a point of bright spot which is giving me a dark spot in diffraction, and 3 lambda by 2 is a point of dark spot which is giving a bright spot to me in diffraction experiment. So in my previous class, I have spent a good amount of time in making you understand, even though it is not there in the book, but I spent a good amount of time to make you understand how diffraction works, how single slit diffraction works, and why is the fringes pattern fading out when we are going away. I explained to you central bright is formed by 100% of the waves, whereas first bright is formed by only 33% of the waves, and the second bright is formed by only 20% of the waves. And as you go away from central bright, the amount of waves contributing for the bright spot formation is reducing, finally fading away. So these things we have discussed in the previous class. Today, let us start. One small topic is remaining, polarization. Very less asked in the examination, but what is asked, I'll tell you today how the questions are coming from here. Very small, simple topic. And mainly today we're going to start dual nature of matter. That is important chapter. Again, scoring simple chapter. So first give the heading as polarization of light from wave optics. Polarization of light. What is the meaning of the word polarization? Have you seen, we have some polarized glasses? They are using in the, sunlight. We are using polarizers. So basically, we are using polarized glasses, polarizers, when we are going out in sun and we have too much of brightness outside. So basically, it cools your eyes. If you are wearing some good quality lenses, see why we are calling this lenses as coolers. They'll say no, wear your sun coolers. Have you seen cooling glass coolers? How this name comes, coolers, cooling glass? Is it cold? It is cold. Does it make you cool? Nothing like that. But why it is called as coolers? Because it reduces the brightness of the incident radiation. And if it is reducing the brightness, obviously it will make your eyes a bit cooler. Cooler in the sense it will not, strain your eyes. So how are these cooling glasses made? By using polarizers inside the lenses. Now, how does this polarizer work? And what is this polarization phenomena? Let us learn that. So, you know by now, if you have electromagnetic waves, which are only giving you all the sunlight, it is visible rays, infrared rays, gamma, all these rays are electromagnetic wave spectrum. Am I right? So, electromagnetic waves are those which are having electric field and magnetic field oscillating perpendicular to each other. And they are also oscillating perpendicular to direction of propagation. Am I right? If you have a wave where the waves are oscillating perpendicular to each other and also oscillating perpendicular to direction of propagation, that is only electromagnetic wave. Now, for example, if you have something like this, a wave which has one wave like this, another wave in different plane like this. This is a wave moving in forward direction. Now, this wave, if I want to remove one wave, for example, let this wave be called as wave A and let this be called as wave B. If I wish to remove wave B, what I can do? I can put in front of it a device where this alone will come out. Which will come out after this? Only A wave will come out, because B will get objected by this, isn't it? Or if somebody keeps a device which has opening like this, then what is going to come out? Only this is going to come out. Am I right? And A is going to get eliminated. These kind of devices are called as polarizers or polaroids, whatever you want to call it. Polaroids, or sometimes called as polarizers. So by this itself you can understand what is polarization phenomena. Polarization phenomena means reducing the intensity of the incident radiation by cutting off some waves, isn't it? So first you draw this diagram and I'll give the definition to you. First you please draw this diagram of these polaroids or polarizers. Then I'll give you the definition of it. Please copy down the diagram. Let me know if you are done copying the diagram. I hope everybody is realizing they are in different planes. This is in a different plane, okay? That is, wave A is in XY plane if you say, then plane B may be in XZ plane. And by using a polarizer, in the case A, that is in the first case, I have removed wave B. In the second case, I have removed wave A, isn't it? By using polarization. Now give the definition, right? The definition of the phenomena of polarization, right? The phenomena of restricting the oscillations of the wave, or you can write the oscillations of a transverse wave, oscillations of a wave only in one direction, is known as polarization, is known as polarization. Okay, now please pay attention, I'll give time for copying. Suppose, just to draw it simply, I am drawing a wave where, see how the particles are vibrating, so you can understand how it is moving. And if I am drawing this kind of dots, it means that we also have vibrations in the plane of the board. That is, particles vibrating like this also, up and down also, and particles vibrating into the plane, out of the plane also. Are you getting a point? The particles vibrating like this also and like this also, isn't it? So in front of this wave, if I keep a polarizer or a polaroid which has opening like this, okay, what will happen? What I'm going to get as output? I am going to get the output like this, isn't it? Do you agree with me or not, guys? Because this direction wave, the wave which was vibrating in the plane of the paper, got eliminated. Now I keep another, I will not call it as polarizer, it is actually called as analyzer. Okay, if I am going to keep the analyzer, I have two options once again. I can keep like this, the same way it was kept earlier, which will not make any effect, the same thing will come out. Or I can even keep it like this, opposite to that. What will happen? Nothing will come out, no wave will come out. Am I right? This is one condition. Another condition can be if I keep like this. What will happen? The same thing will come out. This is called as an analyzer. So basically, please pay attention. Basically, intensity of the radiation is depending upon the angle between polarizer and analyzer. Please pay attention, guys. If polarizer and analyzer are parallel to each other, then intensity remains the same before polarization and after polarization. Whereas, if polarizer and analyzer are perpendicular to each other, the intensity of the light became zero after it passed through analyzer. Are you able to feel that? This thing only was given by a scientist, his name was Malu. So the law is called as Malu's law. I don't know it is there in NCERT or not, the name is there or not, but Malu's law says that I is proportional to cos square theta, which will make I equal to I naught into cos square theta. Now this formula helps us to find what is the intensity of the radiation after it has passed through polarizer and analyzer. And what is theta? Theta is the angle between polarizer and analyzer. Polarizer and analyzer. And what is I naught? I naught is peak intensity or maximum intensity. And now you can see very clearly here theta became 0. And what is cos 0? 1. So what is I? I same I naught. If this was I naught, maximum intensity, after passing through analyzer, if theta was 0, angle between polarizer and analyzer was 0, then what ray came out? Same thing what entered came out. But if the angle between polarizer and analyzer is 90 degree, what is cos 90? 0. What will be I? 0. Nothing came out of this. This only is given in NCERT also, I think. This formula is given in NCERT, right? I is equal to I naught cos square theta is given or not in NCERT? I think somewhere it is given. Is it given? I think it is given. So copy it fast. Copy it fast, please. Copy it fast. That is not from polarization, Thambi. That formula is from interference itself. That is the basics of constructive and destructive interference. I told this to you also. If A1 is there, A2 is there, then net A becomes A1 plus A2. But I1 is there, I2 is there, then net I becomes root I1 plus root I2 the whole square. From there only what you are saying comes, that concept comes, 4I into cos square 5 by 2. Not from polarization, don't confuse, okay? If you are done copying, then let us not wait further. Let us start the next chapter. Why to waste time? This is all about this chapter, guys. That is from the wave optics chapter. What can come is YDSC is a very important part. Diffraction is another important part. And very less questions coming from polarization. And before YDSC, I taught about the basics of Huygens principle. Very important. What is wavefront? What is secondary wavelet? What is the law of reflection by using wave optics? Law of refraction by using wave optics? Then talking about the basic of principle of superposition, where I taught to you at which phase difference or at which path difference we get bright spot and dark spot, and why do we get bright spot and why do we get dark spot. So all these things are very important from this chapter, and that's where the question comes from. Numericals based upon YDSC is very important. Please practice those, then only you will become confident in this chapter. Give the next heading as dual nature of matter and radiation. Next heading is next chapter, which is dual nature of radiation and matter. Of radiation and matter. From this chapter, before I start taking the chapter, let me tell you what is important from here, from exam point of view. What are the topics that is going to be asked in the examination and what you should focus on more. Let me talk about that. So no doubt the most important part of this chapter, from where the questions are certainly going to come in the board examination, is from the graphs. Today we will focus on this. There are 4 graphs. Each graph has its own importance, and the questions are going to definitely come from graphs. Graph drawn between the photoelectric current and the potential for varying intensity, constant frequency, or varying frequency, constant intensity. All these graphs, how it is drawn, how it comes, theory behind it, it's definitely important for the board examination. Second important topic in this chapter is Einstein's photoelectric equation, the very famous equation for which Albert Einstein even got Nobel Prize. Einstein's Nobel Prize is not in E is equal to mc square. His Nobel Prize is in Photoelectric equation. Very famous equation. This equation also you can expect the question to come in the board examination. So the main part of this chapter is these two only, and the questions are mainly coming from either graphs or from photoelectric equation of that is radiation. Then last topic, and it also is important, is about de Broglie's wavelength. It is about de Broglie's wavelength. Lambda is equal to h by mv, which you already learned in chemistry in structure of atom in 11th standard. I will once again teach you that topic. These are three most important parts of this chapter, from where the questions are frequently asked in the board examination. Okay, we'll start one by one. And first, let us understand this chapter's basics. And the first topic in this chapter is work function. Give the heading as work function. Phi naught is called as work function. So let me ask a question to you before I start my topic. The question is, all of you know that metals are having free electrons on it, isn't it? Which are responsible for metals to be conductors. So metals are conductors because they have free electrons moving on the surface of the metal, and that only is conducting all the current in the conductor, even the heat. So if this electron is free, why don't it jump from the surface? It does not have. One way of saying it, I'll say in another way. Imagine there is a surface, there is an electron, and somehow it jumped from here. Somehow, assume. If it is jumping from here, it is only possible if it is leaving a positive cavity here. Do you agree with me? If electron is coming, it will leave positive cavity. Now, positive cavity is going to attract back the electron. There is going to be a potential energy between the electron and the positive cavity it creates while going from there. This potential energy is holding it back and not letting it leave the metallic surface. Are you getting what I am trying to say? So if you want this electron to somehow come out of the metallic surface, what you have to do? You have to supply energy strong enough to overcome this potential energy between the electron and the positive hole. If you are able to give that energy, it will easily come out and start roaming. Roaming in the sense it will come out of the metallic surface. I hope you get my point. So what is that minimum energy required to eject an electron from the metallic surface is known as work function of any metal. Write the heading, write a definition. The minimum energy required, the minimum energy required to eject an electron, minimum energy required to eject an electron from the metallic surface, is known as the work function. Of the metal, is known as the work function of the metal, which means that every metal will have its own work function. Some metals will have more work function. It means it needs more energy to make the electron come out, and some metals will have a low work function where less energy itself can make the electron to come out. I hope you get my point. For example, cesium has least work function. I don't know the value exactly, 2.65. How much it is? Anybody knows the value? In book it will be given, guys. And platinum has the highest work function. I think it is 5 point something. I don't remember the value, guys. 5 point something is electron volt is for platinum, and cesium it is 2.62 if I'm right, or something like that. 2 point something, it is 5 point something electron volts. See, now in the modern physics chapter, for energy, unit will be always electron volts. SI unit is joule. SI unit of energy is what? Joules. But we are going to use electron volt, and always remember 1 electron volt is equal to 1.6 times 10 to the power minus 19 joules. And whenever you see the word MeV, mega electron volt or million electron volt, it will be 10 to the power 6 times of EV. Okay, don't forget these things. What is for cesium? Anybody could find it? It's not there in the book. It should be definitely there in the book. You're not able to find it. Anybody who can tell me work function? Very bad. Work function of cesium nobody can see in the book. I guess it is 2.62 if I am right. Let me verify it from the book. Be given actually. Yeah, it is given 2.14 and platinum is 5.65. 2.14 is for cesium and 5.65 is for platinum. Different sodium will have its own, potassium will have its own, every metal will have its own. But why I am bothered about these two is one is having the lowest, one is having the highest. Cesium has the lowest work function, platinum has the highest work function. So no other element. It means whichever element you take, and if you supply 1.5 EV, nothing will come out because no metal is having less than 2.14. Are you getting my point? And if you are supplying an energy of almost 6 electron volts, whichever metal you take, it will eject the electron because work function is more than that for all the elements. That is about the work function. Okay. Now I spoke about ejecting of electron, and I spoke about if electron will be ejected, you have to supply some energy to it, isn't it? Give the next heading as methods of electron ejection. Methods of electron ejection. Methods of electron ejection. How to eject the electrons. There are many ways you can eject. The most simple way can be using thermal energy. Using thermal energy. What will you do for thermal energy? Heat the element. If you're heating the element, you're supplying energy. If energy is supplied, after a lot of vibration because of the heat energy, it may get ejected. That kind of ejection is called as thermal ejection or thermal energy ejection. And in this effect, the electron coming out is called as thermions. Why thermions? Because it has been ejected by the help of thermal energy. That's why it is called as thermions. Same way, another way is electric field emission. They will say also emission sometimes. So thermal emission we can say it instead of thermal energy. I can say thermal emission. And second is electric field emission. Electric field emission. What is that? We know very well that if you have electric field, how you can give electric field? Keeping two plates, plus sigma and minus sigma. In between, if I keep a plate, then plus sigma will attract the electron towards itself and minus sigma will repel the electron on the metal surface. This electron, when it is going to come out by a strong electric field, is called as electric field emission. Are you getting my point? Basic thing. Keep a metal in the electric field. If electric field is strong enough to make electron come out of the metallic surface, that emission is called as electric field emission. Third is secondary emissions. Now what is secondary emissions? Sometimes you can tap it, have a hammer, beat the element. We don't do it generally, but we can do it. If you give some energy by using some vibrations, some hitting by a hammer, that also can release some electrons sometimes for metals like cesium or some lower functional metals. That is called as secondary emission. And the fourth one, the most important one, and what the whole chapter is based upon, is called as photoelectric emission. The last one is photoelectric emission. Photoelectric emission. What is photoelectric emission? As the name says, photo means photons. Photons means light. So if you have light hitting a metal plate, light, when it comes, it brings with it energy in packets called as h nu. Are you aware about that? E is equal to h nu. H is called as Planck's constant. What is the value of it? Minus 34. Planck's constant. And nu is called as frequency of the incident radiation. Frequency of incident radiation. So if this energy is supplied to the element, that is to the metal, and this energy the electron absorbs and comes out of the metallic surface, these electrons will be called as photoelectrons. It will be called as photoelectrons, and this effect is called as photoelectric effect. Okay. So what is photoelectrons? The electrons that are ejected when the light energy of sufficient frequency or threshold frequency is incident on a metallic plate, and the electrons ejected are called as photoelectrons. And if electron is coming out, it will make current. That current will be called as photoelectric current. Are you getting my point? So basically this is the fourth emission, which is called as photoelectric emission, which happens when light of sufficient frequency is incident on a metallic surface. Okay. So after this, give the heading as photoelectric effect. Let me start the photoelectric effect concept itself. Photoelectric effect. So let us start that. Shall I? I hope you have copied this. If you have copied this, I am going to the next page now, where I am going to start talking about the photoelectric effect. And you know who did this photoelectric effect experiment? Loudly. Einstein not did the experiment. Einstein just followed the result. Who did the experiment? His students, very famous names. Hertz. No man, not Hertz. See, always the people who are doing the experiment are not becoming famous. Like in the atoms chapter I told you, Giger and Marsden. Everybody knows Rutherford. Hardly people know about Giger and Marsden. Who did the experiment was Giger and Marsden only. Same way, the photoelectric effect experiment was done by Halveck and Lenard. So give the heading as Halveck and Lenard's experiment. What you gave the heading as photoelectric effect? It is by Halveck and Lenard experiment. Halveck and Lenard experiment. Halveck and Lenard. These two students of Einstein, they did all the setup and they did the research by which they could understand the photoelectric emission concept itself. So I'll tell you about the setup of that. Now you pay attention on seeing what I'm doing. I'll give time for copying. Please pay attention. Okay. So what we did, he took some CRT. CRT means cathode ray tube, and he made some kind of setup like this, where he had one emitter plate and he had collector plate connected like this. You can put a galvanometer here if you want to check the current comes or not. Very basic, simple setup I am telling. If you see NCERT, some advanced setup is given. I will talk about that also. But now I am talking only about the basic experimental setup, where we have an opening from opening we can make the incident radiation to come inside, and then this plate is the metallic plate where the light will hit. This plate is called as emitter plate. It is emitter plate, and this plate is called as, what is this, acceptor plate you can say, or what is the name here exact? Collector plate. Okay, tell what is good for you, can use the name collector plate. Okay, so imagine light of sufficient energy. When I'm using the word sufficient energy, you know what is the meaning? Threshold frequency. You know, every color of light has its own frequency, isn't it? Do you think that each frequency will give same energy? Definitely not. The formula is E is equal to h nu. If E is equal to h nu and we want a minimum energy for ejection of electron, h is a constant, so minimum energy will make minimum frequency also. So minimum frequency which is needed to eject an electron from the metallic surface, that frequency is called as threshold frequency. Write down somewhere. You can write the minimum frequency required to eject an electron from metallic surface. Minimum frequency required to eject an electron from the metallic surface. To eject an electron from the metallic surface is known as threshold frequency. So common sense says that work function will become equal to h nu naught, where nu naught will be the threshold frequency, isn't it? Because at this minimum frequency, what energy you supply will be called as what? Work function. Just before time I gave you the definition of work function. Work function was the minimum energy required. So when you multiply the threshold frequency with Planck's constant, then what you get is called as work function. Imagine you are supplying energy more than the work function. What will happen? Electron will not only get ejected, rather it will also have some velocity. Because suppose energy required for the electron to get ejected is 10 joules. You gave 30 joules. For coming out, it needs only 10 joules. How much you gave? 30 joules. It has 20 joule extra. What will it do with that extra energy? With this extra energy, it will start to move. It will have kinetic energy. So whenever you supply energy which is more than the threshold frequency work function, that energy will be used for kinetic energy of the electrons. I hope you're understanding this very basic concept. Now, what happens, as I said you, if I hit the light which is having a frequency more than the threshold frequency, then electrons will get ejected. Am I right? And these electrons are going to get ejected, and if they are able to make to the collector plate, then we have circuit getting completed, and then you are going to have some deflection in the galvanometer, stating that some current came. Why did I use galvanometer, not the ammeter? Because very feeble current will come. Don't expect 10 ampere, 5 ampere current to come. So very small current will come, which will not be measured by ammeter itself. That's why I used galvanometer, so that even a small current is visible by us on the galvanometer. Okay, this is a very simple experiment which says that whenever we are hitting emitter plate with a frequency of radiation more than the threshold frequency, we are able to see the ejection of electron, which is proved by the deflection of galvanometer. Okay, then a graph was drawn. The first graph was drawn. This graph was drawn between the photoelectric current and number of photoelectrons. Basically, I should say intensity of radiation. Photoelectric current and intensity of radiation. Intensity of incident radiation. One important thing before I move ahead. In this chapter, two words we are going to use very oftenly. One word will be intensity of radiation. Second word will be frequency of radiation. Whenever I use the word intensity, in layman's language, you can understand that brightness I am talking. Something about the brightness. Whenever I use the word frequency, I am talking about the color. So when I say that frequency of incident radiation is changed, it means the color is changing. White, not white, blue, green, yellow, red, orange, like that. When I say that intensity is changing, imagine that brightness is changing. 100-watt bulb, 200-watt bulb, 300-watt bulb, imagine like that. So intensity changing means brightness changing. Frequency changing means color changing. Don't write this in the examination, just to make you understand I am saying this. Frequency means color, intensity means brightness. Okay, coming back. So for a particular frequency, which is more than threshold frequency, if I keep on changing the intensity of the incident radiation, we observed that the graph is a directly proportional straight line graph, which says that as the intensity of incident radiation is increased, photoelectric current is increasing. Photoelectric current, when it can increase? If we have more amount of photoelectrons getting ejected. Less photoelectrons, less current. More photoelectrons, more current. I is equal to NEAVD. If N becomes more, we have more current. So, understand that intensity of incident radiation, it means it is affecting number of photoelectrons emitted per second. Very important. See, keywords are damn important here. So number of photoelectrons emitted per second is controlled by whom? Is controlled by intensity of the radiation. So more intensity means what? More number of photoelectrons emitted, and less intensity means less number of photoelectrons emitted. Are you getting? And since more photoelectrons are getting emitted, by the intensity increasing, current also is increasing. This is the first most simple basic graph of the photoelectric effect, where the graph is drawn between what and what? Intensity of the incident radiation and photoelectric current. And we find that as the intensity is increased, the photoelectric current also increases, indicating that intensity is directly depending upon number of photoelectrons emitted per second. Copy it fast before I go to the next graph. Please copy it.
Sir,
Tell me, man. Andrew.
what is the collector plate and emitter plate, sir?
Can you be a little louder once again?
What is collector plate and emitter plate?
Emitter plate is that plate from where the electrons are getting ejected, and collector plate is that plate where the electrons are getting collected, because electron has to move from this plate to this plate if we want to see some deflection in the galvanometer. Only if the current is moving, we will have some current here, isn't it? So for the current to move, emitter plate is the plate from where the electron is getting emitted. How? Since the light of sufficient frequency is hitting the plate, and these electrons that is getting ejected are going to collector plate. If they are not able to go to collector plate, no deflection in galvanometer. If galvanometer is deflecting, it means the electrons are able to make to the collector plate. I hope you get the point. Yeah.
Sir,
Yes. Please.
sir, in the question threshold frequency format is given, sir,
Hmm.
and then frequency of the wave is given, sir.
Hmm.
If the frequency of the wave is greater than threshold frequency, so
Hmm.
we'll be adding 1/2 of this, sir.
Then whatever energy the electron is going to have will be having some kinetic energy also.
How to calculate it?
Half mv square. Half mv square will become equal to h nu minus h nu naught. H nu will give you energy of incident radiation. H nu naught will give you work function. And what is the energy remaining? Half mv max square. So it's a kinetic energy. What you told actually is Einstein photoelectric equation. What you told now, that only is one big topic, important topic, that is Einstein's photoelectric equation. H nu is equal to h nu naught plus half mv square. Okay, we'll talk about that. Have you copied this graph? If you have copied this graph, then let us talk about the other two graphs which are really very important, shall we? Okay, now please pay attention and see what I am going to do. So everybody, next two graphs are very important because the questions are going to be asked from there only in the board exam mainly. See here. What I do now, I make an additional circuit for this, secondary circuit we call it. So now whatever circuit I have, in that I am not providing any external potential. Am I right? There is no potential provided. I am connecting a secondary potential in the circuit. How I do that? See here, very simple. If I make a setup like this, and I have one jockey here, and I have another jockey here. So now if you see, I have point A, I have point B, I have point C, and I have point D. Why I not connected it? I have two options now. I can connect A with C, B with D, or I can connect A with D and B with C. Both options I have. Why I want to have both the options? Because if I connect A with C and B with D, see what will happen? Your emitter plate will become negative and your collector plate will become positive. If this plate becomes negative, this plate becomes positive, it will speed up the effect. Electron coming out, it will attract it. This plate will push it. Are you getting? This plate is negative, it will repel the electron. This plate is positive, it will attract the electron. So the moment the photoelectric effect starts, if you start increasing the potential by connecting A with C and B with D, you are going to favor the photoelectric effect. Am I right? Because what electron comes out, you are giving energy to it. How? By connecting the battery, the source of EMF. If I connect A with D and B with C, what will happen? A with D means this plate will become positive, this plate will become negative. What we are doing? Opposing the photoelectric effect. Electron came out, negative plate will push it, positive plate will catch it. It won't let it go to the collector plate. What will happen? It will reduce the photoelectric effect. Am I right? So connecting A with C and B with D will give a positive potential, increasing the photoelectric current, and connecting A with D and B with C will give me negative potential, decreasing the photoelectric current. Why I do all these things? To understand the behavior of intensity and frequency. So first what I do, give the heading as how the NCERT gives, same way we can give. NCERT book is there. Yeah. So first heading you give as effect of potential on photoelectric current. Effect of potential on photoelectric current. Effect of potential on photoelectric current. In bracket you can write varying intensity and constant frequency. Varying intensity and constant frequency. In bracket you can write varying intensity and constant frequency. Varying intensity and constant frequency. So the graph is plotted between potential and photoelectric current. So please pay attention here now. So I'm going to plot a graph between what and what? I'm going to plot a graph between photoelectric current and the potential. Okay. So everybody, next 10-15 minutes are very important for listening. So don't start sleeping inside. Pay attention. Some theoretical thing, but very interesting and important thing. When I say zero potential, what does it mean? It means I am not connecting the secondary circuit, isn't it? No potential given. If it is zero potential, first of all, I have given the heading as varying intensity and a fixed frequency. Obviously, frequency is more than the threshold frequency. Varying intensity means I am taking suppose three different intensities, I1, I2, I3, where suppose I1 is more than I2 is more than I3. Just before some time you learned the graph where you understood that intensity is directly proportional to the photoelectric current. So more the intensity, more the photoelectric current, less the intensity, less the photoelectric current. I1 is more than I2, I2 is more than I3. It means that I1 will be somewhere here, sorry, I3 will be somewhere here, I2 somewhere here, and I1 somewhere here. Am I right? Since I1 has the maximum intensity, it will have maximum current, and I3 has the least intensity, it will have the least current because least number of photoelectrons coming out. Do you agree with me? Obviously, at zero potential also, I will have current because of photoelectric effect. Some current is going to be there, but less current. And that current will be more for the first intensity because first intensity is the maximum intensity. So you can imagine like a blue color light is supplied with 100 watt, 200 watt and 500 watt brightness. Can you imagine like that? Because three intensities, I1 is 500, I2 is 200, I3 is 100. And single frequency means suppose blue color light, single color light. What we observed, you see. I'll explain this to you later why it happened, but what was the observation? Understand that first. So first observation is that, I'm writing it here first, I1 more than I2 more than I3. Yeah. So as the, okay, now what do I do? I connect A with, I hope you are able to hear me. Am I audible? Kirti, Anshul, Ivan?
Yes, sir.
Yeah. There was network glitch. 1 second. Yeah. So something very important we are discussing. So when we connect A with C and B with D, I am going to have positive potential supporting photoelectric effect. So as the potential is increasing, we saw that the current also increases, then becomes saturated. Same way for second intensity, increases, becomes saturated. And here also increases, becomes saturated. Meaning of saturation is further increasing of potential is not increasing my photoelectric current. I'll tell about why. I'll tell. First understand what is observation. I'll give the explanation to you later. So this is the observation. Observation is if I increase the potentials, for example, I gave 1 volt, 2 volt, 3 volt, 5 volt, 10 volt battery, then first it increased, and beyond that, whatever increase I am doing in the potential, current is not increasing, it becomes constant. Okay. Then what this Halbach and Lennard did, they wanted to make the photoelectric current to be zero. How is it possible? If you reverse the connection, what connection you want to give now? You want to give a connection like A to D and B to C. If I give this connection, what happens? My emitter plate becomes positive, collector plate becomes negative. It is stopping the photoelectric effect. See, concept is that energy is there because of the photoelectric emission, and now we are supplying energy to oppose it, because you know that potential is energy. How I am saying this? The formula is, remember, U is equal to Q into V from second chapter. Potential energy is charge times potential. So if you are giving some potential, actually you are giving some potential energy to it. That potential energy is stopping the kinetic energy of the electrons. In that case, what is going to happen? It is going to reduce. So I3 reduced at a particular voltage called as stopping potential. This V0 is called as what potential? Stopping potential. The current became zero. The current has become 0. If I see for the second, it also reduced. again became 0. Surprising thing was same potential. If to make the third intensity 0, I needed 20 volts of potential. For making I2 to be 0 also, I needed the same 20 volt potential. And to make I3 also, I needed the same 20 volt potential. Now that was the point of surprise, where we are expecting different values of potential, stopping potential, but we are getting that all the three cases. In one case I have more photoelectrons, in one case I have less photoelectrons, but the same are requiring same amount of stopping potential. This all graph was drawn by Halweg and Leonard, and they were given for observation to Mr. Albert Einstein. So what did he observe from this? What were the conclusions drawn by him? That is very important. Pay attention what happened. It indicates that in I3, I am having suppose 100 watt. Just for understanding, imagine 100 electrons came out. Okay. 200 watts, 200 electrons came out, and 500 watts, 500 electrons came out. So obviously, I1 has more electrons, I2 has less electrons, I3 has least electrons. Okay. But the energy required to stop them is same. I just now told that this potential becomes energy, QV, isn't it? If energy required to stop all these three intensities same, it very clearly means that how much energy the electron was possessing also is same in all three things. If how much energy you are needed to stop the electron is same for all these three, it means the energy they possessed was also same in all three, which indicates that intensity of incident radiation is increasing the number of photoelectrons, but the maximum kinetic energy possessed by an electron does not change. For example, I have 100 electrons. Do you think 100 electrons will have same energy? Never. I'll tell why that also I'll tell why. Because if there is a metal surface, all the electrons will not be in the top layer, right? Some electron is here, some electron is here, some electron is here, some electron is here. If I am giving incident radiation, this electron will come out with less energy for work function. But this electron may need more energy to come out. It means it will have less kinetic energy. So if you have 100 electrons coming out, don't think 100 electrons will have same kinetic energy, because some electron would have come out from a deeper depth. It needed more energy to come out, and less energy is remaining for becoming kinetic energy. So 100 electrons are there. Some electron may have only 1 joule energy, some may have 5 joule energy, some may have 10 joule energy also. Are you getting my point? Out of 100 electrons, it may vary from 0, 1, 2 to let us assume till 10 joule. Same way, when I gave 200 watt of brightness intensity, I had 200 electrons coming out. But the range of kinetic energy is same once again. Some are having 1, some are having 2, some are having 5. Maximum how much they are having? 10 joule only. In I1, I have 500 watts of intensity. 500 electrons came out. But what is the range of a kinetic energy? Same, 0 to 10 joule only. That's why what we are needing to stop it is also 10 joule for all three. Are you getting the observation? The observation says that different intensities of incident radiation means different numbers of photoelectrons getting ejected. But the maximum kinetic energy possessed by the electrons remains same for all the intensities. That's why the energy required to stop them is also same for all three. Are you understanding why it became same for all three? Now, why the saturation happened, that also we'll learn. When you give more potential, obviously more current. What is happening? How current is increasing? See, electron came out, electron has to reach here, isn't it? If all the electrons went there, then why will the current further increase? 100 electrons came out. Without giving any potential, out of 100, only 5 were reaching. Less current only was coming. You gave potential, you supported the photoelectric effect. Instead of 5, 20, 25, 30 were going. You increased potential, 50 were going. Further increased, 70 were going. Further increased, 100 is going. All 100 went now. Increase further. Will the current increase? No. Because all the electrons that got ejected went to the collector plate. So it becomes saturated. Why it is different for different intensity saturation? Because in second case I have 200 electrons. In third case I have 500 electrons. So we need more energy to send it to that collector plate. Are you getting what I'm trying to tell? That's why saturation current, the potential is same, but the current is different for all three. Because here we have 500 electrons, here we have 200 electrons, and here we have only 100 electrons. So if you have listened to my last 10 minutes, now you are clear in this graph. How the graph has been drawn, why the graph is straight line, saturation is happening, why the solid potential is the same. All these things I spoke in last 15 minutes. You can ask Sharan, what do you want to ask? Yeah. Stop. See, we're not saying like that. We should say that intensity governs only number of photoelectrons emitted, but the maximum kinetic energy possessed by the photoelectrons does not change. That's why they have same stopping potential, because kinetic energy is same. That's why the amount of energy required to stop them is also same, because whatever we will supply, this V we are supplying is getting converted into energy only, EV. Q into E means EV in this case, isn't it? That's what is happening. So first you draw the graph, then I'll give some story also, that is some statement also. Please draw the graph. If you have drawn the graph, yeah, tell me you one, something you are asking. See, I said that, please pay attention even. Yeah, I said that when you are increasing the potential, then the electrons are able to go more fastly in the collector plate. Why? Also I said, see, imagine there was no potential connected across. Then what happened? If 100 electrons came out by the photoelectric effect, all the 100 electrons may not be able to reach there, because all the 100 electrons may not have sufficient kinetic energy. I said before some time that all the electrons coming out will not have same kinetic energy. Some may have more kinetic energy, they may go there. Some may have less kinetic energy, they may not be able to go there itself. Right, Yuvan? So if I give external potential, I am supporting photoelectric effect by sending the electrons on the collector plate. So if I increase the potential, more number of electrons are able to go. So without potential, if suppose only 5 electrons are going, if I applied potential, 10 electrons may go. Further increasing potential, 20 may go, 50 may go, 80 may go. All the 100% electrons may go at what particular value. That value is only called as saturation, because if you further increase potential, there is no electron remaining to travel there itself. Then why will the current increase? Are you getting Yuvan? Yeah. And even though the potential is same, but why is the photoelectric current different for 3 intensities? Because in these 3 intensities, the number of photoelectrons came is different. In I1 we have more photoelectrons, in I3 we have the less photoelectrons. That's why they are having different current values. But saturation takes place at a common potential only. I hope it is clear to you. If it is clear to you, and if you have drawn the graph, let me give you some small paragraph of what is to be retained from this lecture. Shall I? Shall I give the theory part? Right? Increasing the intensity of incident radiation, increasing the intensity of incident radiation, increasing the intensity of incident radiation increases the number of photoelectrons emitted per second, increases the number of photoelectrons emitted per second, but the kinetic energy possessed by the electrons, but the maximum kinetic energy, not the kinetic energy, but the maximum kinetic energy possessed by the electrons, maximum kinetic energy possessed by the electrons remains the same, remains the same. Remains the same. Change the paragraph and write, that is the reason, that is the reason the energy needed, the energy needed, the energy needed to stop them, to stop them is also same for all the three intensities, is also same for all the three intensities, making the same stopping potential, making the same value of stopping potential, making the same value of stopping potential. One more thing we understand here, please pay attention. What we understand, that what energy you are supplying is EV naught, am I right? For stopping I am saying. So EV naught must be equal to half mv max square, isn't it? See, again, very conceptual thing I am telling, pay attention. If I supply some potential, okay, suppose stopping potential was 30 volts, I am supplying 10 volts. In 10 volts, some energy was given, EV naught, and that's why, see, the current has reduced. Without this 10 volts, negative 10 volts, it had this much current. But since you gave 10 volts in negative direction, it has reduced the current now. Are you able to understand this? Because whatever energy you supplied, in this case, you supplied EV. EV would have reduced half mv max square, half mv square, not max square. So I said you 100 electrons came out. In that, some electron is having 10 joule, some is having 8, some is having 6, some is having 5, some is having 4, 3, 2, 1. I gave 3 joule energy externally. All the electrons having 3 joule of kinetic energy stopped. But still, electrons having 4 joule, 5 joule, 7 joule, 8 joule, 10 joule are moving. That's why current is there still, some value is there of current. I gave more energy. What happened? Suppose I gave all up to 8 joule of energy. So up to 8 joule, whatever electrons were there, stopped. Only the electrons having more than 8 joule till 10 joule remained. Are you getting the point? And the moment you gave the same 10 joule, which is the maximum kinetic energy possessed by the electrons, all the electrons stopped. That is why in the second case, I gave 2 joule. For 2 joule, whatever electrons were there, they stopped. So then the current reduced. I gave 6 joule. Whatever was there till 6 joule stopped. Current further reduced. I gave 10 joule. That is the maximum kinetic energy they are possessing. Completely current stopped. So at 6 joule, these two will have different values only, right? At 6 joule, if I draw a line, this graph has a different current, this graph has a different current. But at 10 joule, they both will have same value. These things are conceptual. Okay, what I am speaking now. Today, if it is going in your good memory, you'll remember it, or else you'll forget this. That's why I'm telling today's class, be attentive. It's simple, but you should retain in the good memory, that is long-term memory. Interesting thing also. I don't know how much you are getting interest. To me, it is very interesting, this theory. Okay, shall I proceed further? I have to give the next heading as, what is the next graph in NCERT book? What is the heading NCERT book gives? I'll take out, show me.
Sir,
Yeah. Tell
how
man.
EV naught is equal to half MB max square, sir.
See, what is EV naught? EV naught is the energy we are supplying to stop the electrons. Am I right? So, energy you want to stop the electrons must be equal to what is the maximum kinetic energy they are possessing, isn't it? So, how do you find the maximum kinetic energy? Kinetic energy formula is half mv square. So, maximum kinetic energy will be half mv max square.
Oh,
Are you getting a point? And what is EV naught? EV naught is potential energy. How it is being given? By the use of battery. So, energy that you are giving to stop the electron, if you want to stop all the electrons, it must be equal to what? The maximum kinetic energy is half mv max square. Is it clear, Andrew?
yes, sir.
Yes, if it is clear. Next heading is effect of frequency. Effect of frequency of incident radiation on stopping potential. Effect of frequency of incident radiation on stopping potential. On stopping potential. In bracket you can write, for varying frequency and constant intensity. For varying frequency and constant intensity. Varying frequency and constant intensity. What does it mean? It means that now you are going to have different frequencies like nu1, nu2, nu3, but it will have common intensity. You have green light, blue light, yellow light of 100 watt each, but making sure that the frequency of incident radiation is more than the threshold frequency. If threshold frequency is 10 hertz, I am giving 15 hertz, 20 hertz, 25 hertz. And what I observed that at zero potential, which means there is no potential applied, this A and B are connectionless. There is no connection between A and B like this. Then I saw the frequency which is maximum has maximum photoelectric current. This is photoelectric current and obviously this is potential. Okay. Then what I did, I increased the potential. Okay. I increased the potential. It means I connected with A with C, B with D. So my emitter plate became negative, collector plate became positive, supporting my photoelectric current. So I saw that the frequency started to, that is the current started to increase, attained a saturation value. Same way for second frequency, when I increased the potential, increased, attained the same saturation current. Same way increased, attained the same saturation current. Now what I did, I changed the polarity, and what I made A to go with what? A to go with D and B to go with C. The moment I made this, what happened? Emitter plate became positive, collector plate became negative, opposing the photoelectric effect. Electron that was getting ejected was being thrown by collector plate and getting absorbed by the emitter plate, opposing the photoelectric effect. And then the current started to reduce at a particular potential. stopped completely. Let this be stopping potential V naught for the first intensity, first frequency. Second frequency had its own stopping potential, and third frequency had its own stopping potential. What is the observation? Observation is, for different frequencies of light, when I try to stop the photoelectric effect, the energy I needed for a greater frequency was more to stop, and the energy I needed for stopping a lesser frequency radiation was less. Second observation is, all three frequencies, even though they are emitting different number of photo current initially, but they are saturating at the same level, same current. Let us understand these two observations. See, frequency is different, but what is same? Intensity is same. Am I right? Intensity governs the number of photoelectron ejected per second, right? I told before some time, intensity is governing how much electrons will come out. Since the energy required to stop in all the three cases are different, very clearly indicating that maximum kinetic energy possessed by these electrons will be different. It has more kinetic energy. That's why we need more energy to stop it. It has less kinetic energy, so less energy. It has least kinetic energy, so least energy to stop it. It means that if you don't have energy, then we also need to supply less energy to stop you, isn't it? So what we understood that frequency of incident radiation, what it governs? It governs the kinetic energy possessed by the electrons. Intensity was governing number of photoelectrons emitted per second. If I used 100 watt of light, 100 electrons came out. 200 watt of light, 200 electrons came out. 500 watt of light, 500 electrons came out. But if I use 100 watt, 50 hertz, 100 hertz, 150 hertz, in all three hertz, if number of electrons coming is 100, it will be 100 only. But in the first case, 50 hertz, 100 electrons are coming, but maximum kinetic energy, suppose is 10 joule. In case of 100 hertz, it may become 20 joules, and in case of 150 hertz, it may be 30 joules. Are you getting what I'm trying to say? More frequency means more maximum kinetic energy being possessed. Since intensity was same, number of electrons was same. Since number of electrons was same, saturation took place in the same level. Again I am repeating, electrons came out. Why we had more photoelectric current for more frequency, you know? Because more frequency means more energy. Without giving this itself, it went. So more frequency of incident radiation. Why is it having more photoelectric current? Even though in three cases the number of electrons coming out is same, but higher frequency is giving more energy to electrons, it is going. Lesser frequency is having less energy, it is not able to travel. So in the third case, we had the maximum photoelectric current. But when I supplied external potential, amount of energy I required to make everything go across the plate was same for all three. Reason is 100 electrons, 100 electrons, 100 electrons. So number of electrons that has to be transferred from emitter to collector plate is same, 100 only in all the three cases. That's why the saturation current value is same for all three. Because how much current can be coming? Only by 100 electrons. And current by 100 electrons is going to be same. I hope you get my point. Next thing is, why we got different stopping potential? Because the maximum kinetic energy possessed in each frequency was not same. In less frequency, the energy also was less. So energy I need to supply also is less. In more frequency, energy that the electrons had was more. So if you want to stop it, I need to supply more energy. That's why the energy required to stop also was more. Is it clear to you? If this is clear to you, copy it fast. I'll give the notes for the observation. Please copy it fast. Let me know if you're done copying the graph. Okay, let us give the theory also then. You can write increasing the frequency of incident radiation, increasing the frequency of incident radiation, increasing the frequency of incident radiation increases the maximum kinetic energy possessed by the electrons, increases the maximum kinetic energy possessed by the electrons, and does not affect the number of photoelectrons emitted per second, and does not affect the number of photoelectrons emitted per second, number of photoelectrons emitted per second. Change the paragraph and write since different frequencies of incident radiation had different energies possessed by the electrons, different energies, you can add kinetic energy basically, different kinetic energy possessed by the electrons, different kinetic energy possessed by the electrons, the amount of energy needed to stop it was also different. The amount of energy needed to stop it is also different. The amount of energy needed to stop is also different. That's why they had different stopping potential. That's why they had different stopping potential. Right. So I hope you understood this. One graph still remains, and photoelectric equation, de Broglie wavelength still remains. Small topics only. Bigger topics we covered today. Okay. So what I have taught to you, hopefully it has gone inside your head. But believe me, you will not remember it for long if you don't study it. Simple thing, but you may forget it. And if you don't want to forget it, go home and read once. NCERT book is simple for this chapter. Read by yourself NCERT book itself. Okay. So we learned today the work function. We learned today what are the various ways to eject the electron, that is emissions. And then we learned about photoelectric effect, the experiment conducted by Halbach and Lenard. And the 2-3 graphs we have learned today. One graph remains. We will learn in the next session. Till then, take care. Bye-bye. We will meet again in the next class. Good night, everybody.
Thank you, sir.
Take care. Take care. Bye bye. Take care.